let's see, last time we finished our section all the DC circuits, so now we're going to move into magnetism and Faraday's law and things like that. So technically we have 5 lectures left, but everybody seemed okay with the idea of canceling that last one on Monday. That takes us down to 4 lectures. So we'll do the best we can in 4 days. Yeah, so let's do the best we can in the next 4 days we have. Before we get started, does anybody have any questions about anything? No? Okay, so let's go ahead and get started. So I sort of figure you know a little bit about magnetic fields, just from your life and from high school. There is a very, very long history about magnetic fields. It goes back, sort of recorded history, the best we can tell, goes back at least 3,500 years with the first use of a compass. So a long time ago, we've been studying magnetic phenomena. Definitely has been observed across all of the cultures. So sort of all of the humans have observed magnetic fields and figured out how to use them. We developed some modern ideas of magnetic fields. That was in about the early 1800s. So in the early 1800s, we got a whole bunch of physics relating electric fields and magnetic fields. We're going to cover some of that stuff. I would say most of the things that we're interested now about magnetic and electric fields, it's all sort of tech-driven and energy-driven. So those are the biggest reasons we study it now. Those are a lot of the applications we use. If you're looking for some background reading, your textbook's fine. Wikipedia is actually pretty good on the history of magnetism, so that's nice. We'll cover a little tiny bit of this top one, and then mention briefly this one as well. So let's just do a very quick recap of what we did about electric fields. So we said that electric fields surround charges. We represent electric fields with electric field lines. We draw these maps. We know that electric fields start at a positive and go into a negative. We know that we can have a single charge. We can have a proton by itself, or we can have an electron by itself. We know that there are forces between charges where like charges repel and opposite charges attract. Those forces are what we call field forces, or action at a distance, because the things don't have to touch. Let's see, and the density of our electric field lines corresponds to the strength of our electric field. So a strong field here and a weak field here. So that was all stuff we talked about in the electric field section. Now we get magnetic fields. The units of magnetic fields are called Teslas, with a symbol of a capital T. That's for Nikola Tesla. He kind of ranks in probably one of the greatest physicists who ever lives, although I don't think he gets nearly enough glory. He was a Serbian American. He did kinds of things like he thought there should be free electricity for the entire world. And he sort of thought about Wi-Fi way back when. So Tesla was a pretty cool guy. We get magnetic fields in 2 ways. This is kind of interesting. You can get a magnetic field around a permanent magnet, like you stick to your fridge, or around a moving charge or a current. That's sort of interesting. And I would invite you to start thinking about and start wondering about, how are these two kind of the same thing? How is a permanent magnet that you stick on your fridge, how is it kind of the same as a moving charge? So I have an idea, but I'll let you ponder it for a bit, and we'll come back around to that idea eventually. We know that magnets have 2 poles. So when you see a magnet, it often looks like this. You've got a north pole and a south pole. The north pole is the red one, the south pole is the blue one. The north pole of a magnet points close to Earth's geographic north. So the Earth is a giant magnet itself. Because the north pole of a magnet points towards the north pole of the Earth, it means that the north geographic pole of the Earth is actually a south magnetic pole. That's sort of neat. So the Earth looks like a bar magnet where south is up top and north is down bottom. Something interesting about poles of a magnet is we know we can have single charges with fields around a single charge. Theory predicts that you could have a magnetic north pole or a magnetic south pole all by itself. That's called a monopole. Nobody's been able to find those yet. So the theory says it's out there, but we can't find it. So that's sort of interesting. What happens when you take a magnet and break it in half? So if I crack this in half, I would get two smaller magnets, each with its own north and south. If I broke that in half, I would get smaller magnets. I would keep cracking them in half, in half, in half, in half, until I got down to the atomic level, and you would see that the atoms were like little magnets. Okay, so no matter how deep you go, you always have a full magnet with two poles together. So that's kind of interesting. We have the same sort of a field force. Like poles repel, opposite poles attract. If you measure that force, you do find it goes as 1 over r squared, just like the electric force. So that's some stuff in a nutshell. If we wanted to look at magnetic field lines, your textbook has a nice picture, much nicer than I'm capable of drawing. So there's a picture from your textbook. I also brought in a little doodad that we can look at the field lines. So this thing is super old. I'm not sure it's older than me, but I am sure it's older than all of you. It could be older than me, but I don't think so. So it's just a bunch of little arrows. They're magnetic. If I put my magnet on top, you can see the field lines. So the field lines will come out of the north, circle back around, and go into the south. So that's what a single magnet looks like. If I put a north next to a south, you gotta be careful with these. They come out of the north straight into the south. We get some circling around the sides. We can do two norths together. Those lines push away from each other. That's kind of neat. And then I grabbed a stack of rare earth magnets, because I think those are cool too. So those field lines just kind of radiate straight out because I got a pole right at the bottom there. And then it flips around if I go onto the bottom. And then if you put it sideways, it looks like a bar magnet. Anyway, anybody who would like to play with this a little later on, it is up there at the front. So our magnetic field lines, that's what those arrows were tracing out there. So those arrows were showing the fields at specific places. Magnetic field lines go out of a north and into a south. Our field lines don't ever cross. And that makes sense because we can't have a field line that points in two directions at the same time. And if it crossed, that's what that would mean. Like the electric field lines, places where the field lines are close together means the field is really strong. So in close to the poles, we have a strong field. As we get further away from the magnets, the lines are spread out and we have a weak field. So that same kind of behavior. Any questions about that stuff? So one thing I think is really neat about magnetic fields is a lot of animals have magnetoreception. What that means is, like, you know, when you stand up, you can feel the pull of gravity on you, and if you fall down, you sort of fall down and you feel gravity pulling on you. A lot of animals feel the magnetic field sort of the same way we have the sense of gravity. So they have a sense of where the magnetic fields are. So animals, like homing pigeons, this is how homing pigeons work. They can follow magnetic field lines to know where they're going. Same thing with whales. They follow magnetic field lines, at least partially, in the oceans to get to where they need to go during the migration patterns. Ants and bees do it too. Turtles and fish, so here's a turtle going down to the beach. They follow magnetic field lines to kind of navigate across beaches so they can follow the field lines. I have heard, I've never tested this because I only have one dog, but I think it would be really interesting if you could gather a bunch of people with a bunch of dogs. Apparently if you have your dog out and the dog is not on the leash, the dog will line up north to south to do its business. Apparently that's true. So if you could gather enough of you with enough animals and you could just take your dog out for a while with a compass, there's a study you could get published, right? You could definitely show that that's true. So I think that's kind of nifty. Apparently also cows will line up along the magnetic field lines to graze in a field, so you'll see them all polarized in the field. This little guy here, I think this is so interesting. So this is a little bacteria that lives in the ocean. It doesn't have any eyes or anything, so it can't see, it doesn't know where it was. And even if it had eyes, it couldn't see because it lives at the bottom of the ocean and there's no light. And this little bacteria needs a certain level of oxygen to survive. If it goes too deep or too high, it just can't live because it's the wrong amount of oxygen in the water. So this little dark bit right here is a little bit of iron inside the bacteria. The iron lines up on the magnetic field line, and he follows that line to get to the right spot in the ocean. So I think that's pretty cool. That's not really something we study in Physics 1051. That's kind of maybe a little bit more biology or something. But to me, that's just a little bit too cool not to talk about. And then somehow, I think this relates really neat with the Earth, and this might be more geosciences. Every so often, and we're kind of overdue by tens of thousands of years now, every so often the Earth's poles flip. Okay, so I think 120,000 years ago, our geographic north was a magnetic north, and then it flipped. We're long overdue for it to flip again. So I kind of wonder, how does that affect the animals?
North to south just split?
Yeah, north and south flips every so often.
How is that possible?
That's an excellent question. Yeah, so interesting stuff. Loads and loads of interesting stuff there. I'm not trying to drive people into earth sciences, but I bet you there's lots of interesting stuff in earth sciences.
Doesn't it have to do with the rotating axis around the sun, because the sun has its own magnetic pole, so the that way based off the way the axes are looking?
Maybe, yeah, I don't know. I'm not sure it's really well understood. There's also the molten core of the Earth spinning around inside, so stuff happens there too. Yeah.
If the Earth doesn't spin, it accommodates that, I presume.
No. The field is just along for the ride, right? The Earth spins and the field is what it is. So anyway, super interesting stuff. Okay, so now let's get on to the stuff that we do study in Physics 1051. We know, and we studied this for quite a while in the first part of the course, that if we place a charge Q in an electric field, which is made by some other source charge, then it's going to feel an electric force. And we know that the electric force is that charge times the electric field. Our charge can be positive or negative. The force is either in the same direction as the field or the opposite direction. We also know, and you all did this in your last lab, that if we place a moving charge, and another term for moving charge is just current. If we place a moving charge in a magnetic field, it's going to experience a magnetic force. So you made your coil of wire, you let current flow through it, you set it on top of a magnet, and you saw it spin. That's this effect right here. So the moving charge was the current, it was near the magnet, it was in a field, it felt a force, and it spun around. So that's an observational effect. We definitely see that that's true. So should maybe even highlight some of this stuff. The word moving is important. Moving charge in a magnetic field will experience a magnetic force. Okay, and to me this bit's really important. Right, it specifies a moving charge. When you turn the current off, the motor stopped spinning. So that's kind of interesting. So when we do some experiments on charges in magnetic fields, things we find is that we can find the magnetic force on a positive moving charge. So we'll start our discussion about a positive charge. If it's moving with velocity v in a magnetic field, the first thing we notice is that the size of the force is proportional to the size of the charge, how fast it's going, and the size of the magnetic field. So all of these things are important. If we increase the charge, the speed, or the field, we will increase the force. Those are things you could have solved with your motor experiment. If you turn up the current, or if you put in more magnets, the thing would spin faster. Okay, so that's something we can observe. Another thing we can observe is that if the velocity of the charge and the magnetic field of the magnet are parallel, so if our vectors v and b are parallel, our magnetic force is actually 0. Where you might have seen this in your lab, if your coil was flat, if it was parallel to the magnet, it didn't spin, and maybe you needed to get some help or you figured it out by yourself, that you had to twist it so your coil was upright. So if it was flat, it wouldn't spin, but if it was upright, it would. So our next result is that if v and b are perpendicular, then our magnetic force is a maximum. So our conclusion here is that the magnetic force depends on the angle between v and b. So we started by talking about positive charge. If our charge is negative, then our force is in the opposite direction. So everything flips by 180 if the charge is negative. Same magnitude, opposite direction. So we can take all of these experimental results and we can write our expression for the magnetic force is that our magnetic force is our charge Q, where we include the sign of the charge, it could be positive or negative, times V cross B. So this is called a cross product or a vector product. When we did electric flux and some other things, we used the idea of a scalar product or a dot product. The scalar product is when you multiply two things and get a scalar for your answer. The vector product or the cross product is when you multiply two vectors and you get a vector for your answer. People doing physics 2050 are probably really practiced with this. If you're not doing 2050, math 2050, you might not be quite as practiced, but I'll take you through the things you need to know to be able to use cross product in this course. So here's our cross product method. The other way we can find our force is we can say that the magnitude of the magnetic force is the size of the charge times the speed times b times the sine of the angle between v and b. That gives us the magnitude of the force. To get your direction, you have to use your right-hand rule. Your right-hand rule applies to a positive charge. So I'm going to draw a positive charge in the palm of this hand. When you use a right-hand rule, you may have a different way of doing it depending on what you learned in high school. I'll go by what your book does. So force is QV cross B. Your thumb is your first vector, that's V. Your index finger is your next vector, that's B, so V cross B. You stick out your middle finger perpendicular to both of those, that's your result, that's your force. So V cross B is your force. Whenever you talk to physicists, say something about a coordinate system, you'll see people do this all the time. Okay, so as soon as you start to draw things and you do these kinds of vectors, you'll see people do this, and that's what they're doing, is they're looking at this right-hand rule. There are other right-hand rules where you're pointing your fingers and you're sweeping them and you're sticking out your thumb. There are a lot of those. If you have a right-hand rule that works for you and gets you to the correct answer, and you don't like my right-hand rule, you don't have to use mine, just be confident in your own. The other question I get a little bit is, but I learned a left-hand rule in high school, can't I just use that? So people do ask that a fair bit. My response to that question is, you're all grown-ups, I can't tell you what to do. I recommend you switch to a right-hand rule. It is the only rule you will see from now on, I guess unless you want to be a high school physics teacher and then you'll use left-hand rule again. So I recommend you go with the right-hand rule, but I'm not here to make you do anything. Okay, questions here? Yep.
Force is always going to be on the plane, or the plane that isn't expressed in F and B, correct?
Yeah, force is always perpendicular to V and B, because your middle finger comes out from both of these. Yeah, so it's always perpendicular to both V and B, always. I think it's worth just taking a moment to think about just how weird this is. Like, this is really kind of strange. Let's think about the field that we're most familiar with, gravity. So if gravity forces were like magnetic forces, the first thing it would mean is that as soon as you stopped moving, there would be no more gravity and you would be able to float. Okay, that would be weird, right? So magnetic force only kicks in if you start to move. Gravity definitely does that. Then the next thing is if you decided to move parallel to gravity, so just kind of crouch down or jump up, you would still get no force. Okay, so you could move parallel to gravity all you wanted. There would be no force acting on you, so still no gravity. But as soon as you stepped sideways, you would fall on your face, forward on your face. Okay, that would be a very strange world. I sort of think that would be worthy of some sort of sci-fi novel. You know, if gravity was like magnetic forces, what kind of world would we live in? Okay, that is another tangent, but it's still worth thinking about because magnetic forces are really weird. Okay, these are a strange force. They don't act like anything else we've encountered so far. You get a lot into the nitty-gritty of this and why it's so weird in Physics 2750, so you would see more details about that in that course. So let's get into some practice. We'll do both the math way and the right-hand rule way. So our first example, first thing we'll mention is notation. I don't think we've introduced 3D notation yet in this course. So if positive x is to the right and positive y is up, then positive z is out of the page. So an x, y, z coordinate system always follows this right-hand rule as well, x, y, and z. If z is out of the page, we need a notation for out of the page. The way we draw out of the page is a little circle with a dot inside of it. And where that notation comes from is we imagine a dart or an arrow. If it's coming towards us, we just see the tip of the arrow. So that's what this is. If we're pointing into the page, away from us, then we're looking at the flights on the dart, and that looks like an X. So into the page is an X inside the circle. So that's a new notation for us. So let's do example 1. Let's do the right-hand rule first, then we'll do the math second. So if we have a positive charge moving to the right in a magnetic field that points up, what would be the direction of the magnetic field? Okay, so everybody should do this with me because the only way to get good at this is to do it. So your V is your thumb. So your thumb should be pointing towards that wall. Your magnetic field is your B. B should be towards the ceiling. And then what is your middle finger doing? Should be poking you right in the face. Okay, so the magnetic force, F, comes right out towards you in your face. That is out of the page. That is your FB. Okay, so on the paper, you do V cross B, and then F comes up towards you pointing in your face. If we went the route of the cross product, and this is always an appropriate strategy, especially for people who prefer to do math things versus right-hand rule things, in our math way, we would say that our F is equal to Q, that's positive. V is to the right, so to the right is the positive X direction, that's I hat. Crossed with the direction of magnetic field, that's up, that's the Y direction, that's J hat. So the direction of the magnetic force is in the direction of I cross J. There are different ways to know what I cross J is. Some people just remember these things. The way I do it, my first year physics prof showed me, and I never forgot it since, is you put I, J, and K in a triangle, and you point from one to the other. Okay, so if you're in Math 2050, you might have seen this. When you go the right way around the circles, when you go with the arrows, you get I cross J is positive K. If you go the wrong way, you get negative, and if you do something cross itself, that's 0. Okay, so that's example 1. Now let's do example 2. Example 2, we've got a negative charge. So we'll do our right-hand rule. Your thumb goes with V, your finger goes with B, and then your middle finger, your force, points straight at you. Is that the correct answer? No, what do we have to do to get the right answer? Flip it by 180 degrees, because we've got a negative charge here. So your right-hand rule applies to a positive charge. If you have a negative charge, you got to rotate by 180 to get your final answer. So this one is negative, and magnetic force is into the page. We can do that with the math. Our charge is negative. V is in the X direction. B is in the J direction. I cross J is K. So our force is in the negative K direction. Yeah?
I can't remember if I'm just conflating this with something else, but isn't left-hand rule for negative charges and right-hand rule for positive charges?
No, because you never do a left-hand rule.
Oh, I thought in high school I remember doing something.
Yeah, that's what high school does. I recommend you do a right-hand rule, and if you have a negative charge, you rotate your answer.
Yeah.
But as I said before, I can't tell you what to do.
I think it's still right.
Yeah. I can recommend to you that you stick with the right-hand rule.
So does that mean that velocity is also traveling in the opposite direction?
Nope, velocity is to the right. Magnetic field is up.
Force, if
Your
you
force
track your-
on a positive charge would be out of the page, but this isn't positive, so you're rotating your force.
Just the force.
Yeah.
Okay.
So once you get out of the page, you rotate that by 180 degrees. Okay, 2 more examples. So example number 3, you do this one and tell me the answer, and we'll see if we get some agreement. So the X here for the V means V is into the page. V is pointing this way. Okay, so the first answer I got was up. Do we have agreement with up? Some agreement with up. Any disagreement?
And the force is into the page?
Okay, I got an into the page. Any agreement with into the page?
No, I'm asking, velocity is into the page there?
Yeah, velocity is into the page. Okay, I got an answer for down. Does anybody like down? Okay, I got a tiny nod for down. Okay, let's do it. So V is into the page. Your thumb is into the page. And then do what you gotta do. I'm gonna walk around like this. But your index finger has to point towards that wall. So V has gotta be into the screen, and B has to point towards that wall, so your index finger has to be that way. So whatever you gotta do with your hand or your body to twist around is what you need to do. You extend your middle finger, see what it's doing. So here's where our answer of up came from, because our finger does point up, but then we have to catch that that was a negative charge. And a negative charge, we've got to rotate by 180 degrees, and it actually points down. My trick is, if you're doing this on a test, if I'm here like this, I can't move my wrist. I'm not that agile. I can, however, move my paper. So twist your sheet of paper around, right? Your thumb goes into the page, your B goes like this, your finger is pointing towards the top of the page, but it's a negative charge, we know that's wrong, so it has to go towards the bottom of the page. Okay, so feel free to twist your page around if you can't twist your body around. We can do this with the math. Okay, our charge is negative, so there's a negative. Our V is into the page, that's a negative K direction. We're crossing that with B, which is to the left, that's a negative I direction. Okay, this is about as tangly as this can get, so let's deal with all these negatives. A negative times a negative times a negative is a negative. So negative times negative is positive, and I've still got that negative out front. So I'm left with negative k cross I. If we like the triangle, we can do the triangle. K cross I comes around the circle the right way. It gives us a j that is the negative j direction or down. Okay, so either way you like, right-hand rule or math way, they should give the same answer. If you were doing this on an assignment, you might want to do both ways just to confirm your answer. It doesn't take long to do both ways. Okay, are we good to hear? Okay, how about our direction of force, for example, 4?
Maybe 0.
Okay, the fastest answer I got was 0. Does anybody else like 0? Okay, a few nods for 0. Anybody with different answers? Okay, so this is 0. So V is parallel to B. This was our experimental observation that the force was 0. In terms of our math, we've got a positive charge. V points up, that's the j direction. B points up, that's the j direction. Something cross itself is 0. Okay? And then if you're thinking in terms of right-hand rule, you can't do that, right? Your thumb can't point in the same direction as your index finger. That's sort of a, a reminder that it's 0.
So if there's a magnetic field somewhere on Earth, can you stop it if you manage to put the velocity in the same direction as the magnetic field?
Yeah, if the velocity is in the same direction, then it won't feel a magnetic force.
That's only for moving charges.
For
right?
moving charges.
Right,
Okay, so let's do an example with a little bit more to it than just the right-hand rule. So in this example, I have a charge moving in a magnetic field. Magnetic field has a magnitude of 0.75 Teslas. We see in the picture that it points straight up. My positive charge is moving with a speed of 450 meters per second, and it's at an angle of 26 degrees, and my Q is 1 microcoulomb. So we can do this in one of two ways. We can do magnitude and direction, or we could do the cross product. To do the cross product wouldn't be that difficult, but you would have to break your velocity into components. So let's just try magnitude and direction and see if that one's a little bit more straightforward. So if we did magnitude and direction, then the magnitude of the magnetic force is the magnitude of the charge times the speed times the magnitude of the field times the sine of the angle between them. We do have all of these numbers. And we get that the size of the magnetic field is 1.48 times 10 to the minus 4 newtons. Then to find the direction, we'll put our thumb in the direction of V, our index finger in the direction of B, and then we ask, what does our middle finger do? It points straight out of the page. That's the K direction, or you could write out of the page. Either is fine. So our magnetic force as a vector has a direction of K for out of page. Okay, questions here? No, so far so good. So, let's ask a conceptual question. I've got a negative charge that I'm shooting in, it's moving to the right. Is it going to follow path 1, path 2, or path 3? Let you think about it and then we'll see.
The X represents the direction of the field.
Right, so these X's are the direction of the magnetic field. It points into the page. So the people doing their right-hand rule are the ones I'm guessing who are going to get the right answer. so I think I got 2 concurrent answers of down, which I guess you mean path 3.
Yeah.
Anybody else agree with 3? Do you have a different answer? Okay, so let's see if we can apply the right-hand rule. So V is to the right. Our index finger is our magnetic field into the page. Our extended middle finger is the magnetic force. So my finger is pointing towards the top of the page. That would be the force on a positive charge, but this one is negative. So the force on my negative charge here points down. If it's a downward force, it's going to deflect downwards. So it will follow path 3. So the people who said downward, absolutely right.
What difference does it make? Why does it go down or up depending on the charge? The magnetic field is perpendicular to the luminous particle.
Right, so V is this way.
The velocity is traveling this way.
Yep,
The
magnetic field
is this way.
into the page. Yep,
Force is either up or down.
either up or down. It's up if it's a positive charge. It's down if it's a negative charge.
There's a positive plate at the bottom, is the best way to look at it. So it's either being repelled if it's a positive, so.
No, there's no positive plates.
I'm just saying, it's like that's the way that the field moving is the same as a negative plate at the bottom.
No, but there's no electric field here. It's only magnetic field.
Sorry, but I was saying in the sense of an electron, it's moving the same, similar direction. As if there was a positive plate, it's either being repelled by the magnetic field or attracted, isn't it?
You could reproduce this motion if there were electric fields here. Yes, that's true, but there aren't electric fields here.
Yeah, I was
Yeah.
just saying to envision it, an easier way to understand why it's moving.
You gotta be careful that if you're in the middle of the test and we start talking about electric fields here, then I think you don't understand what's happening.
No, it's just because they're similar.
Yeah, you could definitely, and in fact, we'll get to an example where we do have both magnetic and electric fields.
That's purely magnetic.
But this is only magnetic fields and only a magnetic force. Right, so there's your velocity, there's your field. If it's positive, it would deflect up. If it's negative, it would deflect down. Right, and this one is negative, so it does deflect down. Okay, yeah, this direction stuff can be a bit tricky. So we've got kind of that general direction stuff done. So let's look at a special case. What if we had all 3 vectors being perpendicular? Okay, so in this example, back here, V and B weren't exactly perpendicular. They were in the same plane, but not perpendicular. But what if they are perpendicular? What happens then? So we know that our magnetic force, FB, is QV cross B. And like someone pointed out earlier, I don't remember exactly who, if your F is your middle finger and V and B are your thumb and your index finger, this was you, I think, said that, it means your force is perpendicular to both of them. So your force is always perpendicular to V and always perpendicular to B. With force perpendicular to velocity, this should maybe ring a bell from one of your sections from Physics 1050 or 1020, so where force and velocity are perpendicular. And let's look at the motion. So here we've got a picture of a positive charge moving straight up. The magnetic field is into the page, so V and B are perpendicular. It means the force points, let's see, V is this way, B is this way, force is going to be strictly to the left. There's our magnetic force. There's FB. This force is to the left, so the charge is going to drift partly upwards because it's moving up, and it's going to drift partly leftwards. So it's going to move along a path that takes us up and left. So a little bit of time later, it's going to be right here. It's going to be moving up and left, so the velocity is going to look like this. We do our right-hand rule again. V cross B gives us our force. That force is always perpendicular, FB. So it's pulling it around some more. It gets up here. The velocity is this way. Does it look more familiar now? This is circular motion. Anytime you have force perpendicular to velocity, the result is circular motion. So this will result in circular motion.
Centrifugal force,
Uh,
acceleration.
So centripetal motion is normally what we call it. Centrifugal force is generally going to make physicists get upset.
Yeah, sorry.
Circular motion. We do in fact have a special name for it when it's a charged particle moving in a magnetic field. Then we call it cyclotron motion. So a moving charge in a magnetic field that follows a circular path, which is what happens when V and B are perpendicular, we call that cyclotron motion. We do know how to analyze things that are moving in a circle because in physics 1050 or 1020 you learned about circular motion and you learned that A was V squared over R. We're going to layer that here in this problem. So on our moving charge, the sum of the forces is mass times acceleration. Typically with these charges, they are very tiny. We do neglect the weight. So the only force with an appreciable magnitude is going to be our magnetic force. Is equal to m times a. Our magnetic force, FB, is the magnitude of the charge times the magnitude of the velocity times the magnitude of the field times the sine of the angle between them. That's the angle between B and B. That's 90 degrees, and sine of 90 is equal to 1. And then acceleration is v squared over r. So we'll put those things in our equation. QVB equals m times v squared over r. We can simplify a little bit. We can solve for different things. I've got a v on one side, a v squared on the other side. I'm going to divide both sides by v. And one result we often write is that v is equal to m, the mass, times v, the speed, divided by the charge, times the magnetic field. This is the radius of a charged particle in a magnetic field.
If V and B are multiplied together get 0, then how does the force not 0?
No, v times b is not 0. It's qvb times sine theta, right? So it's the magnitude of charge times the magnitude of speed times the magnitude of the field times the sine of the angle between them. The angle between v and b is 90 degrees, and sine of 90 is 1. Nothing here is 0.
Right.
Is the radius of the particle, the radius of the path it takes?
Right, it's the radius of this circular path.
Oh, okay.
Yeah, let's put that on the diagram because that is a good thing to have in there. Yeah, good question. Yep.
Is this how like satellites in orbit kind of operate?
We get the same sort of behavior. So satellites in orbit, you have a gravitational force, which is perpendicular to the velocity, and that makes things go around. Yeah, so same sort of behavior. This is a picture, also nabbed from your textbook. So you can see this effect, right? This is definitely something you can measure. What's happening in this picture, see if I can zoom in a bit just to make it better. If you've got your book there, you can just open it up and have a look. So right here, these copper colored things are 2 copper wires. They're putting lots of current through it, and what that does is it establishes a magnetic field. So we're going to come to current carrying wires making fields. But these 2 sets of wires make a magnetic field. This thing right here, this is a glass chamber, and it's filled with gas. So it's just a big ball, you know, it's yay big. It's full of a gas. Then on this side, we have what's called an electron gun. So it heats up an iode, which shoots off a pile of electrons, which comes into this gas. So we've got electrons, that's a charge. We're shooting them out of a gun, that's motion, and they're in a magnetic field. The velocity and the field are perpendicular, so we do get circular motion. This light right here, that's the electrons colliding with the gas. When they smash, they give off energy, and they give off energy in the form of light. So this glow is showing the path of the electrons in that magnetic field. So one of the experiments you can do is just shoot charged particles in, measure the radius of the path, and then you can use this idea to do some of the analysis for the mass and the charge of those particles. It's how you can discover new particles. If you find that sort of thing interesting, you might get in contact with Triumph in BC and see if they would hire you up there. So they've got like this huge cyclotron. They shoot particles in there and speed them up and accelerate them all the time. Okay, still good? So we can take this idea and just take it a step further. And let's ask, what if we have a velocity of a charged particle in a magnetic field, but instead of being purely perpendicular, what if it also had a component that pointed at the page? So part was parallel to the field and part was perpendicular to the field. Here's a picture that gives it away. So what happens is, and I have a very low-tech demo, so if the velocity is perpendicular to the field, that results in circular motion. It does this. If the velocity is parallel to the field, remember, if the velocity and the field are parallel, there is no magnetic force. If there's no force, that component of velocity won't change. So I've got a part of the force makes it go in a circle, and then part of the velocity just keeps going. So it moves in helix. It goes around in a circle as it goes up or down. So you'll get a helical path if you have both components of velocity. So the perpendicular part of the velocity makes circular motion. The parallel bit of velocity is just a drift because there's no force, so it just keeps going with that velocity. And together, it forms a helix. Okay, that idea okay? Okay. So now, my favorite application of this idea is the Northern Lights. So, how many people have seen the Northern Lights? I saw them once, but they weren't that impressive. My mom and dad lived up north for years, and they say it's kind of worth doing in your lifetime, so it's totally on my list. So sometimes you see the Northern Lights, apparently, and it can look like this. It's hard to see that from Newfoundland. Or, no, from the island portion of Newfoundland. I bet you it's spectacular in Labrador. I've never been up there. So what happens with the Northern Lights is the sun far away, particularly if there's some sort of solar storm, charge gets blown off the surface of the sun. So charge will leave the sun. It moves out in all directions, so some of it comes towards the Earth. So we have these streams of charged particles moving towards the Earth. As the charges come towards the Earth, some of it starts to follow the magnetic field lines, okay, because the charges are coming towards the Earth, so they get trapped in the magnetic field lines. The velocity will have two components, part parallel to the field, part perpendicular to the field. The part that's perpendicular will make it going around in a circle. The part that's parallel will just keep it drifting. The magnetic field lines are stronger at the poles, so here the field is stronger and it just gets drawn in and more activity up near the poles. And then, like the electrons in the gas chamber, the charged particles, when they get into the atmosphere, it collides with the molecules in our atmosphere. When it collides with the molecules in the atmosphere, it gives off energy as light. So you see these great little streams of light that show the motion of the charged particles in the air. I think that's really cool. Some people say you can hear it too. I don't know, I'm dubious about the sound. Yeah?
So does that mean that Northern Lights operates similar to how like a particle accelerator would?
Yeah, exactly. Yeah, that's totally right. Yeah, it's cool.
And the sun acts as the accelerator, whereas the fields are the directional operator, or the
Yeah, it's really cool. Yeah, so the sun is the source of the particles, and then it gets trapped in the fields of the earth. Yeah, you're exactly right. Okay, that's all the time we have for today, so we'll quit there, and we'll do kind of more problems starting on Monday.
Are we gonna get our midterms back?
Yeah, I started marking them last night, but then I decided to go to trivia instead.
Fair enough.